Hello, my name is Francisco Del Val, and this is the Eggstronaut challenge for Mechanics 1 Statics. Here's an overview of my project. My objective statement is to design and build a Mars lander prototype that will not exceed 450 grams of weight, which will efficiently prevent an egg from breaking when falling from a distance of 1 meter or higher. These were the design requirements and other requirements for the project. The minimum drop height 1 meter, the maximum weight 450 grams, the maximum landing pad size 300 by 300 millimeters. Research past lander designs, sketch 3 preliminary designs, and use statics and dynamics to find certain values. So here are my materials and supplies: spaghetti, 1 egg, hot glue gun and glue, plastic bag, string, tape measure, and ruler. Here's one of the past lander designs that I researched, the Mars exploration rovers, the lander structure. It has 3 pedals that are connected to a tetrahedron base, weighs 375 pounds on Earth and 140 pounds on Mars. Takes 3 hours to retract its airbags and deploy the lander pedals. Here's a picture to it on the right. Here's the other lander that I researched. It's the Mars Insight lander. It was built on NASA's Mars Phoenix lander, weighs 794 pounds and has 2 solar panels. And here are the dimensions. The length is 19 feet and 8 inches and the width is 5 feet and 1 inch. Here's a picture to it on the right. This is design 1 for the lander prototype. It is a cube structure with 4 legs, 4 airbags, and a parachute. Here are some pros and cons. I'm going to begin with the pros first. It has the Eggstronaut at a higher elevation than the legs, contains 4 legs that will take on the force of the impact. Each leg has 3 supports, includes 4 airbags and a parachute. And here's the only con to it. The Eggstronaut is not in a stable structure, can fall from the lander. This is design 2 for the lander prototype. It is a cube with a wing-like structure, 2 airbags, and a parachute. Here are some pros and cons. It has the Eggstronaut at a higher elevation than the base, has a dynamic design with a wing-like structure, contains 2 airbags and a parachute. And here are 2 cons. The Eggstronaut is not in a stable structure, can fall from the lander, doesn't contain any support legs, only the base. This is design number 3 for the lander prototype. I wanted to go on a different design with 2 airbags, a cross structure in the middle, and a parachute. Here are the pros and cons. The pros are that it has the Eggstronaut at a higher elevation than the base, has 2 horizontal structures to protect the Eggstronaut, contains 2 airbags and a parachute, and here's the con, doesn't contain any support legs, only the base. I was having trouble with the other designs making a stable structure for the egg. I thought that the airbags would help, but I was really concerned about it falling from the lander or breaking at impact, so I went for a more simpler design in design number 4. It has a parachute. Here are the pros and cons. The pros are that it has the Eggstronaut at a higher elevation than the base. The Eggstronaut is held in a stable structure. It has a base with 4 legs that can take on the force of the impact. It contains a parachute, and here's a con. It doesn't contain any airbags. This was my final design for the lander. I based it off design number 4, which was simple to make. I made each structure member 10 spaghettis thick and 7.5 centimeters long. Here's the weight of the lander, 122.47 grams, which was below the requirement. The dimensions are 95 millimeters times 75 millimeters times 220 millimeters. And the reason why it was 95 millimeters was because of the glue. From where I glued them, it made it longer. Here's the front view and the back view of my lander. The top view and the side view of my lander. We then go to dynamics. We need to find the final velocity at impact. So here's the velocity question that I used. Final velocity squared equals initial velocity squared plus 2 times acceleration times distance. I listed my knowns and unknowns, as you can see. I plugged in the variables that I knew and I just solved for velocity. So at the end, the final velocity was 4.43 meters per second, as you can see. I then use the conservation of energy equations. The initial potential and kinetic energy are equal to the final potential and kinetic energy. Potential energy is equal to mass times gravity times height. Kinetic energy is equal to half times the mass times the velocity squared, and work is equal to the energy at impact, which is equal to force times height. I listed my knowns and unknowns. I then solved for each value. So as you can see, the potential energy was 1.2 joules, the kinetic energy was equal to 1.2 joules, and the work was equal to 1.2 joules, making the conservation of energy equation true, meaning that at the initial, the potential energy was going to be at its highest, which was 1.2 joules, while the kinetic energy was at 0 because it's not at motion. And then the final one was going to be the potential energy was equal to 0, while the kinetic energy was equal to 1.2 joules since it was at motion. And at the end, the work done was 1.2 joules. I then wanted to bring drag into the equation, so I used the force of drag equals to the coefficient of drag times the gas density times the velocity squared over 2 times the area. I listed my knowns and unknowns. I then moved some variables around to find the velocity. As you can see, it was the square root of 2 times the weight times the coefficient of drag times the gas density times the area, and at the end the velocity gave me 2.38 meters per second and the drag force was 1.2. I then used another equation to find the acceleration, and the acceleration at the end was 0 meters per second squared, meaning that the velocity was constant. We then move on to the statics calculations to find the normal force at impact. Force equals ma, so 0.12247 kilograms times negative 9.81 meters per second squared gave me that the Landor force was going to be negative 1.2 newtons and the normal force at impact was going to be 1.2 newtons. The sum of the forces in x, y, and z were all going to be equal to 0, so the sum of the forces in y would be equal to the natural force minus the force of the Landor, so 1.2 newtons minus 1.2 newtons equals 0. The work here at the right shows how I would have distributed the forces throughout the structure of the Landor. So here you can see that negative 1.2 newtons was going to move down, but it distributed into each structure member, meaning that each one was going to be negative 0.3 newtons. But then each point that I added here to the structure was going to be going upwards again from the natural force. So it was going to be 0.3 newtons, meaning that they will all cancel out, having zero force. This was the performance of my lander. Its weight was 122.47 grams. The drop height was 1 meter, and the result was that it passed because it met the design requirements, and the Eggstronaut did survive the 1 meter drop. I provided a video of the drop, but it was recorded in slow motion, so feel free to skip at around 2 or 3 minutes into the future because the video is pretty long, and I'm really sorry about that.
Yeah. Una, dos, tres.
The second test I did was dropping the lander at an increased height. I increased the height into 1.5 meters. The weight stayed the same at 122.47 grams, and the result was partial because it did meet the design requirements, but the Eggstronaut did not survive the drop. Here's a video that I provided for you guys.
Oh, ya sí se quedó.
Ya.
I then used a performance equation that was given to us. Performance equals the drop height divided by the width. So performance of the first test was 1 meter divided by 1.2 newtons, which gave me 0.83 meters per newton. And performance number 2, which was test number 2, was 1.5 meters divided by 1.2 newtons. And performance number 2 was 1.25 meters per newton. This was my conclusion. Were the objectives achieved? They were, because I was able to create a prototype of a lander meeting all the requirements that also protected the Eggstronaut when falling from a distance of 1 meter. What lessons did I learn? That it takes a lot of calculation and step when it comes to creating a structure for the real world. This was made at a smaller scale, but there are a lot of variables that engineers have to take into consideration when working on making equipment for either space travel or for everyday use, such as building a bridge. How would you redesign your lander? To further improve the performance, if I was able to redesign it, I would have made the base stronger by adding a cross horizontally, similar to one of the preliminary sketches that I did. Here are some of the sources that I used for this project, and this concludes my presentation. Thank you.